So the next time I read from a virtual address that happened to be in the same page that I already cached, it's free. It's a hit. It's a cache hit. So that's nice, right? You get all these nice caches. So beautiful when you hit the TLB. But that's the scarce memory, by the way. So if you're doing a lot of virtual mapping and you're all over the place, then older translations will be discarded, will be flushed, and then new addresses will be entered. The finally we're going to talk about is the caching. Of course, the walk, the page walk, this is literally what we explained, is expensive. You don't want to walk the memory every time because while the CPU is starting to read something, like, hey, read X address from memory. I just want to read X address. I don't want to translate in order to read. I try to at least do a little bit translation as possible. And so if you, in order to read a memory, you need to translate the memory, which requires reading from memory to actually translate to get the address to actually read the memory, we'll never finish, right? We'll never be done. So what the CPU does is it takes that knowledge, right, of the walk that says, all right, this page address, virtual address is this physical address. So it skips all of that and caches that as a nice array that we talked about. But it's a very compact, it's a tight cache in the CPU. It's called the TLB, Translation Lookaside Buffer. And in it caches pages mappings, essentially. And it's very efficient, right? Because it knows that it works with a single process, right? And the virtual translation for that process, as long as I'm executing the same process, I can reuse this cache all over again, right? So if I'm, at the moment I read another page, I update my cache. Like, all right, this is this page. So the next time I read from a virtual address that happened to be in the same page that I already cached, it's free. It's a hit. It's a cache hit. So that's nice, right? You get all these nice caches. So beautiful when you hit the TLB. But that's the scarce memory, by the way. So if you're doing a lot of virtual mapping and you're all over the place, then older translations will be discarded, will be flushed, right? And then new addresses will be entered, essentially, to do the translation. So it can get expensive. And I think one of the problems that people noticed in MySQL 8 was this large cache, large code base, which means a massive number of virtual page translation to physical page translation, which exceeded as you're reading from this physical memory and as you're jumping between different pages, the TLB gets full and then you flush it and then you keep walking the page again and then doing back and forth, and that can kind of suffer the performance, because if you have like a large code base, that means all of this has to go in memory. We still have to read that stuff, right? And as you're reading and you're jumping between different places, especially if you have like functions that are all over the place, they're not next to each other in code, then you're reading from different physical places in memory, and that are as opposed to reading like from the stack, right? The stack is beautiful. The TLB loves the stack because most of the stuff is, if you're reading from a function, you're calling another function, is just almost the same page. If it's not the same page, it's the page next to it. So the translations are very similar. So you cached at least some of the stuff, right? So as you're reading through things are contiguous. The locality of data access is so critical here. Right? Compare this to heap accesses, which are almost random. Randomness can create these fragmented TLB entries for the page address translations. So that's fascinating stuff. Yeah. Pop quiz. Process A gets in. TLBs cached right, for all these virtual to physical addresses. Now, kernel does a context switch, brings in process B. Does the TLB remains or no? Can I reuse the TLB that I just cached, all these beautiful virtual addresses? No, you cannot use the TLB for a different process because virtual addresses are unique. Mappings are unique per process. So if I have virtual address, I don't know, 7 in my process that maps to a certain physical address, the same 7 can be mapping to a different physical address for another process, or could be even not mapped. So I cannot use that stale entry. It's a private mappings. So you do not use that at all. You cannot reuse TLB entries for between processes. Between threads, it's amazing. Why? Why? Guess. If I'm switching threads, it's beautiful as long as those threads belong to the same process. Because guess what? It's a shared memory. It's a shared memory, guys. All threads share the same virtual memory space of the parent process. So if I'm switching threads, it's way faster. I get to keep my beautiful TLB. I don't flush it. But if I'm switching processes, I need to flush my TLB. That TLB needs to go. And so you have to rewalk the new page and cache new entries. The exception is kernel pages, which are marked as global. Kernel code is shared between every single process. It's a kernel. It's the kernel. But the kernel has code itself. And the CPU has to read the code to execute system calls, for example, right? And interrupts and whatnot. So in order to do that, well, you cannot, because the kernel also lives in virtual memory. It's the same thing. It has its own virtual memory. It's the same thing, right? Well, if you think about it, the trick that we do in the kernel is the process top part, whatever 99999 or whatever FFFFF until 7 something. All of this is mapped, is reserved for the kernel. So the top part of your process actually mapped to the kernel code. So that's another benefit of the virtual memory. Without you knowing, your part of the process is actually half of it, or the top half is actually for the kernel. And you just map to it. But you as a user, you cannot access the kernel stuff. So it's another shared memory concept. So pages that are, if you're accessing these virtual memory that belong to the kernel, there is a bit in the page table that's called global. It literally says global bit. And the CPU, when it loads the page, it knows that it's a global page. So the TLB entry has the bit set on as a global. So it will not essentially flush those entries because they can be reused. Because it's so beautiful, right? Because the kernel will be walked a lot. So it would be nice to have the kernel pages cached, right? Of course, it takes precious cache space from your TLB, but hey, that's the price we pay, my friends, for all this virtual memory stuff, guys. Yeah. So, of course, it all goes back to the CR3 register in the CPU. Every time I do a context switch, the kernel writes the page table root physical address translation in the CR3 register, so that the CPU just reads the CR3. It doesn't even know. The CPU doesn't know about processes. It doesn't know processes exist. It just hey, all right, someone writes to my CR3. I'm just gonna walk this thing. It just executes code. It doesn't know what's going on. There's no concept of processes when it comes to CPU. It doesn't know. Maybe this changed, but it's an abstraction. It's an operating system abstraction. This processes idea, right? So if I switch a process, I just update the CR3, and now I'm just pointing to a different location in memory and physical memory, which has the page walk that we talked about, the levels, right? And we just walk that. And finally, guys, what I like to also talk about this, I talk about the virtual memory, and you see the complication, right? It's not an easy concept. Take it with a grain of salt. Challenge it. Everything can be broken. All of this stuff. I always like dreamt of building my own kernel, but not a general purpose, a specific kernel just for my needs. I don't need half of the stuff in the kernel. We don't really need if you're building a specific things. All right, it's a general purpose, and anything that's general purpose, you cut corners, right? You do all of this stuff, right? You do all this, like, oh, what if someone do this? What if someone did that? What if someone did that? But I was like dreaming about building a database as a kernel itself. The database talks a database system that is the kernel. There is no operating system. Don't need that. Just database on the metal directly. No virtual memory. Why do I need virtual memory for that? I know my stuff. I'm spinning up my own. There's no processes. I don't even need processes. I have code. I have single process doing everything. Why? Why do you need processes? You imagine the limits you can go to. Unlimited, my friends. Unlimited. We can go. You can go everywhere with this. Just expand your horizon. Everything can be broken. Don't take anything for granted, right? And challenge everything. And even all of this stuff. There's beauty in what we build, but in the same times, you can always challenge that. Take it for what it is. Understand why it was built. Go back to the roots and tweak it back. And build your own stuff.